summary of the laws of mechanics. At least at some point in the course in mechanics, we should say what the basic governing equations are, and then go on to circular motion, which will be a topic which will be with us in some form or another till the end of the semester. So let's just go back to this car problem. We have a car with a stiff suspension, which means it doesn't tip around like this. We're assuming the wheels stay on the ground. We lock the front wheels. The back wheels roll freely, and we want to figure out what the acceleration of the car is. And we're given all the geometry and the coefficient of friction and the gravity constant, and we want to figure this out. So the free body diagram looks like this. The rear wheel, we assume, is massless, so as the car slows down, the torque it takes to slow down the wheel is negligible, so the wheel does its job in that it doesn't resist motion or help motion or anything like that. So there's a vertical reaction here. There's gravity pushing down. There's a friction force here, so we could divide this into a normal force and a friction force times mu, which is the normal force times mu, or we could say the net of those two forces is at a given angle. Those are equivalent expressions because we can give either the friction coefficient or the friction angle. These are equivalent constants which are related by this equation, tangent of phi equals mu. That's if something is sliding. So one way to do this problem is you try to find enough equations and enough unknowns. In this setup, we have this force is unknown. The magnitude of this force is unknown, but not its direction. Had we drawn the free body diagram with an N and an F and a sideways force here, this force would have been unknown. Or if we took this as to mu times N, the N would have been unknown and this would have been implicit. So we have two unknown forces anyway we deal with it, and an unknown acceleration. The acceleration we assume is just in the I direction, and this is why we have this section called the constrained motion in one dimension. We're assuming that these wheels stay on the ground, and this only goes in one direction. Okay, so the setup I did last time until the very end of the class is we have three equations and three unknowns. The mysterious or new equation is angular momentum balance. We can pick any point we want. If we pick this special point up here, where this line of action intersects this line of action, angular momentum balance about this point doesn't include these two forces. These are the unknown forces, so in one equation we get one unknown, or don't we? Okay, so now this is your quiz question. If we start with this equation, what do we get in terms of this result? And let me give you 3 minutes to do that algebra and see what you think. So this is now a test of whether you can execute that equation. And ask me a question if you need to, and you have 3 minutes to do this. So the eye clickers are going to work. You're just not going to see the eye clicker. I'll see it here, and I'll tell you how you do. Why doesn't everybody vote E for starters so I can see how the votes come in? That was fast. Very good. So ask me a question about anything if anything is unclear about what you're supposed to do or anything unclear on the blackboard. You guys in the last 5 rows, I'll leave you there now, but I like it much better when the last 5 rows are empty. So if people in the middle here could make blank seats and the people in the back come forwards for linear momentum. The mechanics tradition, engineering tradition is to call angular momentum H, as opposed to the physics tradition. Does that address your question?
Yes.
Okay, 10 seconds more. Just get in a vote. 5, 4, 3, 2, 1. Lock up the vote. Okay, 108 of you voted. 14 of you voted for A. 39 for B. 26 for C. 6 for D, and 23 for E. The majority of you voted for B, which is what I would call the right answer. So where do we get that right answer from? There are a couple ways to do it intuitively, and then I'll show you the algebra next. Okay, let's do it intuitively. Yes?
How can any of those be the answer if they're not in units of acceleration?
Aha. It should be.
Put G's in all of them. I thought there might be supposed to be G in there.
There's definitely a missing G in all of them. So the right answer is E. Not anymore, but the right answer would have been E. Okay, my mistake. There should have been a G in all of them. Okay, so what's the intuition here? If this was just a car sitting still on the ground, these two forces would be in proportion to these two lengths. This force would be proportional to D over L. Now the question is, if that's the distribution of weight on the tires by the lever rule, that this force is D over L times mg, then you say, well, the friction should be mu times that, and then divide by the mass gives you this result. So this would be the quick intuitive result if you thought the weight distribution on the tires was that what you get in statics. Now how do you know that that can't be the case? Is once there's friction here, that applies a torque. So we had torque balance was satisfied when it was the static situation. Now we've applied a torque here. Torque balance wouldn't be satisfied anymore about the center of mass. So this car, even though it's a dynamics problem, about the center of mass, the torques have to add up to 0 because it's not rotating. So in order to balance the torque, this force needs to be bigger. If this is bigger, then the friction force is bigger proportionally. So the answer here is a B if we put this G back in. Let's just do the calculation in detail so we can do the algebra. What are the sum of moments relative to E? It's the position of all of the relevant forces. These two forces have no net moment relative to E. So it's the position of G relative to E crossed with minus mgj. This is all that we have on the left-hand side, plus 0, plus 0. Any questions about that for the left-hand side of the equation? Now the right-hand side of the equation is new to you, but the right-hand side of the equation has in it the position of G relative to E crossed with the mass times the acceleration of this point G. But the acceleration of this point G, we assume, is just in the I direction, so it's AI. Why is that? It's because the rate of change of angular momentum of any complicated system is that which you would get by thinking of it as a particle, which is just r cross ma, plus the motion of the parts of the system relative to the center of mass. In this case, it's a rigid object. Therefore, all of the parts have no acceleration relative to the center of mass. They all move exactly like the center of mass does. So then to flesh this out, we have to put in what is the position of G relative to E. That position is, we go down a distance, h minus h, and that's in the j direction. And then we go to the right a distance d in the I direction. And then this quantity capital H is equal to the length of the car divided by mu, and that comes from this geometry. Here's this angle phi, here's this angle phi, and so the tangent of phi is L over h, therefore h is L over mu, because mu is tangent of phi. Okay, so then we just have to carry out this cross product. To carry out this cross product, that's the cross product of this quantity with this one. We have a j crossed with j, which is 0. So all we have left over is this one here. So we have an I crossed with j, which is k. So we have a minus mg d in the k direction. So we have minus mg d in the k direction. And then on the right-hand side, we have similar things to deal with. Here we have an I crossed with I, which is 0. So all we have is this term here. So we have minus h j crossed with something times I. J crossed with I is minus k. Minus minus is plus. So we have h minus h a I. And of course, we have to also remember this m, which I forgot when I was doing the multiple choice solution there. Okay, so now this whole thing has a k in it. let's make sure we've got our signs right. We have a minus h minus h. We have a j crossed with I, which is also a minus k, so we have a plus h minus h times a. So that looks right as far as the signs go. So then we can take this quantity here, take the dot product of both sides with k, which just means pulling out the k component, and this gives us minus mgd equals h minus h times a m, which says that the acceleration is equal to, let's see, the m's cancel, and then we have a gd minus gd over h minus h. Does that look right? Then we say, what is this quantity, capital H? This turns into minus g. Then we have a d. This capital H was L over mu. And then we have minus h. So that's our final answer. It accelerates with a negative acceleration if we take A as being positive to the right. How does this compare to the multiple choice answer? Well, when h is equal to 0, we get back our multiple choice answer. The magnitude of the acceleration is just what we would have got from statics. So if you can put the center of mass of the car on the ground, we get back our static solution. On the other hand, if h is above 0, it makes this quantity smaller, it makes the whole expression bigger, which is why this is the correct answer, given that we have the g in here. Now, what are the other sanity checks we can put in? So let's put in sanity checks. So if we put h equals 0, this gives us that the acceleration is equal to mu g times d over L, which is what we kind of expect. When the mass is on the ground, there's no need to redistribute the mass. We don't have any moment from this friction force to balance out. And so the static reasoning gives us the right distribution of the normal forces on the tires. What else can we check? When mu is equal to 0, well, mu goes to 0, this quantity goes to infinity. So this, I really shouldn't put equals 0, but goes to 0. We have A goes to 0. So that seems like a reasonable result as well. There's another funny result here, which is what happens if the geometry is such that this force passes right through this point here. So the center of mass is kind of far forward. That's a funny special case. What would that special case be? It would be that E over H is equal to mu, or tangent of phi. So if E over H is equal to tangent of phi, then we put here that, let's see, we can do this various ways. Let's put H is equal to E over mu. So that turns this into A is equal to minus G D. Then we had L over mu. And then H would be E over mu minus E over mu. Then the mu, we can multiply top and bottom by mu. So that would turn this into minus G mu times, and then on the fraction we'd have D over L minus E. But L minus E is equal to D, so this gives us minus G mu. So in the special case where the friction force would pass right through the center of gravity, that's what this case is here. Friction front wheel force passes through G. In that case, what happens? This force is passing through this point. In order to have angular momentum balance about the center of mass, this force has to be 0, because it's the only force that doesn't pass through this point. So the rear reaction force is 0, which means the whole weight of the car is borne by the front wheel, which means the friction force is the weight of the car multiplied by mu, and the deceleration of the car is just then mu times gravity. So if you move this weight forwards, you get to this critical point where this wheel is on the border of lifting off, and you get the full braking force in the front. So that's why you tend to use front brakes, is because you're tending towards that situation. You have more reaction on the front wheel, not just because the center of mass is forward, but also because of this dynamic effect that even extra weight goes on the front of this. Now what happens if this center of mass is forward of this point, still behind the front wheel, so it's happy in statics? It's no longer happy as a dynamics problem. What we find out if the center of mass was forward at this point is that to keep this car from rotating, we'd have to have suction on this back wheel. This normal force would come out to be negative. Now, it doesn't make sense for it to be negative, which means this thing would lift off, and all of a sudden our assumption of no rotation doesn't make any sense. When do you see this situation? Not so much in cars, but say in bicycles. If the center of mass does tend to be forward of this line, and if you just lock the front wheel of a bicycle, you find yourself going over the front wheel of the handlebars. You don't skid at all, you just tumble over the top. It's a self-locking situation. The front wheel doesn't skid, you just tumble over the top. Okay, any questions about this example? Yes?
Isn't that L over mu minus
L over mu, what did I put here? I put here L over mu, and this is E over mu. Is that what I wanted? H becomes E over mu, and this becomes L minus E. L minus E is equal to D. Is that correct now? Yes? Say again? Well, the assumption the car doesn't rotate shows up here, that we say the acceleration of the center of mass is just in this direction. And it also shows up here, where we say the rate of change of angular momentum is just due to the center of mass, and there's no motion relative to the center of mass. So it shows up in both places. Otherwise, we have to either not know that the acceleration, we don't know the direction of it, and also if there's motion relative to the center of mass, but you have rotation, then there are more terms in this equation here. Does that address your question? Any other questions? Okay, so now let me just do a quick aside on the laws of mechanics, because now we're starting to plug in these laws. So if you look in the front cover of your book, the laws of mechanics are summarized, and really you should sort of know that inside front cover, both of those pages, left and right, inside and out. It's hard to appreciate so far, but now it's getting to a point where you can appreciate it. But the key laws of mechanics are linear momentum balance and angular momentum balance. And what we want to look at is not just for a particle, but for any system. And any system we could think of as a collection of a large number of particles or as a continuum. So you can write the same equations as continuum equations or as discrete equations. So linear momentum balance has to do with forces. So we have all the forces on the system, and the key here is that we put all of the external forces on the system are equal to the sum of all the rates of change of the linear momentum of each of the particles. So you have F equals ma for each particle, and you add up for all the particles, and you get F equals ma for the whole system. When you do that addition, there's all these internal forces, and you assume that they all cancel, that the net of all the internal forces adds to zero, whether they come in equal and opposite pairs or some other reason. You assume the internal forces add to zero, and we get this result. If you want to write it in the continuum form would be the integral over all the mass of the acceleration dm is equal to the rate of change of the system. So these are the same equations. This is thinking of it as a continuum. This is a bunch of particles. And all of this collapses to a beautiful expression like this. So as far as linear momentum balance goes, no matter what the system is, 1 particle, 2 particles, 20 particles, a continuum, a fluid with a solid, anything you want, the sum of the forces on the system is the mass times the acceleration of the center of mass. Total mass times the acceleration of the center of mass. Now for angular momentum balance, which is the more interesting, deeper equation, and actually, in the end, the more useful equation. We have that the sum of moments relative to any point, let's just call it C, is equal to the rate of change of angular momentum. So here we have the rate of change of linear momentum. Here we have the rate of change of angular momentum relative to point C. So one of our headaches, difficulties, technical problems that we will be dealing with is how do we evaluate this quantity here? The left-hand side is just like statics. R cross F, or if they're couples, you put them in directly. The right-hand side is this thing that we have to evaluate. And the general expression, if we want to write it analogous to what we have above, is that we have a summation of all the positions of all the particles relative to point C multiplied by the masses of the particles times the accelerations of the particles. And that's the absolute acceleration. Or if we want to write the continuum version, it's the position of the particles relative to C crossed with the acceleration of each of the particles integrated over dm. Now, the hard part is that this thing does not collapse down to some simple expression. So you would like to think that this collapses down to something simple, because in physics 112, you had F equals ma, and you had torque equals I alpha or J alpha, and those were your two analogous equations. It turns out that that's only a special result, only for rigid objects, and only when you take angular momentum balance about the center of mass. And we want to think of things more generally here. So we do not want to put on the right-hand side J alpha. That's wrong, too narrow, only applies in special situations. So what is the general result here? The general result is that we have the position of the center of mass relative to this point C crossed with the total mass of the system times the acceleration of the center of mass. And that's just what we used in the car problem, plus another term. And that other term is the position of all of the particles relative to the center of mass crossed with the acceleration of each of those particles relative to the center of mass multiplied by the mass added up over all the particles. Or that expression, we could write the continuum version of it, which is the position relative to g crossed with the acceleration relative to g added up dm. If the object is moving like in a rigid way without rotation, then this term is 0 in the car problem. If it's moving in a rigid way with rotation, that thing is just J alpha or I alpha. If it's more complicated motion, then more complicated things happen. And if we're in 3 dimensions, that J alpha term isn't even correct also. That's only a 2-dimensional result. In 3 dimensions, it's a more complicated formula. So in 2D, so for a 2D rigid object, this quantity, and this quantity here, I could call it the angular momentum relative to g. Angular momentum relative to g is equal to the center of the moment of inertia relative to g times the angular acceleration times k. And we're going to get to this. I'm not going to do it now, but next week we're going to drive that and use it. So this is the general story. Why do I tell this to you is because people said, where did that h naught come from? Well, here's where it comes from. This is the general result. If you want to know how do you get from here to here, it's a little bit of vector algebra. You can read about it in the book or try and do it yourself if you're theoretically inclined. Okay, any questions about this? Okay, so why do I put this up here is because this is really what the whole course is about, this thing here. This is in the background. These are the equations we're just using all semester. We started out so far just using this, especially just this in 1 dimension. Now we're getting to where we're using this. Even for these problems with no rotation, like this car problem, angular momentum balance is a useful and needed equation. In the end, when you get good at doing dynamics problems, you will find, just like for statics, that you get farther with angular momentum balance than linear momentum balance, in that you never need to use linear momentum balance. You can always solve all problems with just angular momentum balance. You can derive this equation from this one and not vice versa. Okay, so now I want to go on to a whole new topic, what's the whole new topic is we want to do more complicated motions. So we started the class doing particles in a line to get used to calculus and differential equations and how things change in time in MATLAB and so on. Then we had particles in space, which turned out to be really easy. You just do x and y components separately, and you write the differential equations, and if nothing else, you can solve them in MATLAB, and you can figure out how rockets move, and satellites, and planets, and bullets, and everything else. Then we get to these problems like this car problem, or pulley problems, where we have motion in one dimension, but we have to worry about various constraint forces, either in that one dimension or out of that one dimension. Like here, we can think of those tire reaction forces, constraint forces. Now we want to take an extended object moving in a more complicated way, but before we get to that, we're going to do a special case of a particle moving in a special way. Now we already did a particle moving in a general way. Seems like a special way should be easier. But it turns out that moving in a special way is harder. Why is that? It's just like in this pulley problems. If you add a constraint, the explicit consideration of the constraint makes the problem technically harder. So if I had a particle hanging from a string bouncing around, it does crazy things. Whereas if I have it hanging from a string, it does a simple thing. But that bouncing around case, we just write F equals ma, plug in the spring law, set up the differential equations. The circular case, we have to add in this constraint that the distance of the mass from this hinge is a fixed distance. And all of a sudden, even though it's a simple problem, you would think it technically gets harder because we have to deal with the constraint. So I want you to pay very careful attention. Now I want you to watch this very carefully. I want you to focus on this ball, and I want you to feel relaxed. And I want you to think very deeply about this ball. And when this class is over, you're going to have a deep understanding of how this ball moves. Okay? So rather than set you up with the kinematics and so on, I'm just going to jump into this example of this pendulum, and then we'll pull out the tools we need to do this. So we're going to have this problem, which is a simple pendulum. And how does it look? We've got something hanging on a hinge like this. We've got a mass here like this. We've got some length here like this. We've got gravity down like this. I'm going to pick a funny coordinate system. And the reason I'm going to pick this funny coordinate system is so I can keep things positive and conventional. So I'm going to have an angle here, theta. That's kind of normal. But I'm going to call the x direction down and the y direction over there to the right, so that x, y, and theta are related to each other by all the standard formulas with cosines and sines. Okay, so it's a little funny looking x and y, but it saves us trouble of having to think too hard about sines and cosines and so on. Okay, now the big result we're going to get out of this is that theta double dot is going to equal minus g over L sine theta. So this is going to be our differential equation, which we could write in first order form the following way. Theta dot is equal to a quantity we'll call omega, which is analogous to velocity in the linear problems. And we're going to say omega dot is equal to minus g over L sine theta. So this is what we call the equations of motion. And if we got to this point, we could then figure out how this thing moves by solving these differential equations. So our goal is to get to those differential equations so we can plug them into MATLAB, or you can solve them with pencil and paper. Not. None of you can solve this problem with pencil and paper. James might be able to. This one is just on the edge of what human beings can solve with pencil and paper, and I think it's beyond your edge. It might be inside some people's edge. I'd say it's beyond my edge too. I would never deal with this problem. What's the solution to this differential equation? It doesn't have a simple solution. On the other hand, it's such a common problem, and related to such common problems, that they've given the solution a special name, And I think this is called some kind of elliptic integral is the name of the solution of this differential equation. And you go, what? I thought the pendulum was like the harmonic oscillator. Well, it is like the harmonic oscillator in the limit of small angles, but we don't have the limit of small angles here. So we get this more general differential equation. Now the question is, how do we get to that differential equation? And by the end of this week, you should know how to get to that differential equation maybe 5 different ways. So I want to do this maybe the fastest way I possibly can. How am I going to do that? I am going to draw a free body diagram to start with. So for a free body diagram, I've got this mass, I've got this string, I'm going to cut the string, it's going to have some tension going up to this point here, and I have mg like this, and that's what I got. Now I've got a theta in this problem. This problem only has 1 degree of freedom. It's moving in a plane. It's not moving in a straight line, so I can't just think of it as x and y. But it's only got one way it can move. It can move along an arc. So I can parameterize the motion with a single number theta. So somehow polar coordinates seem kind of natural to this problem. And we can say, let's deal with these polar coordinates by introducing some special vectors, which I'm going to call ER. Sometimes I call it E sub capital R. I don't mean any special difference between either of those. And then a unit vector in this direction, which is E sub theta. And the problem with these guys, the problem meaning the technical difficulty, is these things are not constants. They change as theta changes. So we're going to use these special vectors, these polar coordinate vectors, but these polar coordinate vectors are going to change in time as this particle moves. So now we want to use this in some, say, equations of motion. What equation of motion can we use for this problem? Well, the simplest one to use is to call this point here O, and to use angular momentum balance relative to point O. So write angular momentum balance relative to point O for this system. So what does that give us? It gives us the sum of moments relative to O is equal to H dot relative to O. Something for you to think about in homeworks and exams. Write down the general equation before you start substituting things in. Makes it easier to keep track of. So what do we have? We have the position of the mass. What are we going to call that mass? Let's call this point A. So the position of A relative to O, or I could call it G actually in this case because the center of mass is right at this particle, of G relative to O, crossed with the acceleration of this particle G. Sorry, crossed with minus mg, crossed with mgi, because I picked a coordinate system where I is pointing down. That's the coordinate system I used up there. Then on the right-hand side, I have the position of g with respect to O, crossed with the acceleration times the mass. So this is the mass, and this is the acceleration of g. And now this is just a particle. I'm not thinking of it as an extended mass. So this is all I have. In terms of the big angular momentum balance equation over there, I have the angular momentum balance. The rate of change of angular momentum has to do with the center of mass motion plus the motion relative to the center of mass. All I've got is a particle, so all I've got is that relative to the center of mass. Now, this is the hard part here. What is the acceleration of that center of mass? So what's the position of that g? The position of the g is equal to L times ER. And this is the position of g relative to O. So just stare at this equation for a minute and see if you have any questions about this. At all times, this is going to be the position. Any questions about that? Raise your hand if you're happy with that. Okay. So now we'd like to figure out what's the velocity of this particle, or the velocity relative to O, but I can just call it the velocity because point O is fixed in space. That's the rate of change. So it's R relative to O dot. And now we have to take the time derivative of this thing. Well, L is a constant. So the velocity only has to do with the rate of change of this unit vector, E sub R dot. So we're looking at this unit vector here, E sub R, I'll draw it big. And here's E sub R at some time. Here's E sub R at some later time. What's the rate of change of this? Is this quantity here, delta E sub R. Well, it's that thing divided by delta T. How far does this thing go? What's the change of this thing? It's just this delta theta. And what's the change in this per unit time is delta theta with respect to T. What's the direction of it? This direction over here is orthogonal to E sub R. It's the E sub theta direction. So this quantity here is equal to theta dot E sub theta. This is a key equation. This one equation is probably worth your suffering over. If you don't understand this, you should think about it again and again and again. Try to derive it various ways. This is maybe the quickest intuitive derivation. There are more careful derivations in the book of this, and you can go over those yourselves or ask me and I can do them. So that means that this velocity of g is equal to L theta dot E sub theta. What's that say? It says the velocity of this thing is in that direction, the E sub theta direction. It's bigger if L is bigger, and it's bigger if theta dot is bigger. That makes sense. It's an intuitively correct formula. It's got all the right proportionalities. It's the right direction. It's the right magnitude. Looks like a duck, smells like a duck. It's a duck. Looks like the right velocity, smells like the right velocity. It's the right velocity. Now we want to figure out what the acceleration is. The acceleration of g is the rate of change of the velocity. So that's equal to d by dt of this expression, L theta dot E sub theta. Now we have to use the product rule of differentiation. L is still a constant, so we get L theta double dot E sub theta plus L theta dot E sub theta dot, the rate of change of this E sub theta vector. How does this E sub theta vector change? By exactly the same rules as this E sub R vector. You go from one theta to the next. The direction of the change of E sub theta is the minus E sub R direction, and its rate of change is proportional to theta dot. So we have E sub theta dot is equal to minus theta dot E sub R. And then that tells us then that the acceleration of this quantity g is equal to L theta double dot E sub theta minus L theta dot squared E sub R. So this is what they call the centripetal acceleration, something like that. Now we've got this acceleration. It's ready to plug into equation 1. So now we go back to equation 1. We also substitute in this acceleration. On the left-hand side, we have L E sub R. So we have L E sub R crossed with mgi. And on the right-hand side, we have L E sub R crossed with this acceleration times the mass. The acceleration is L theta double dot E sub theta minus L theta dot squared E sub R, that centripetal term. That centripetal term has no effect on this equation because we're taking a cross product of E sub R with E sub R, which is 0. So on the right-hand side, we get L squared theta double dot M, L squared M theta double dot. And this gets multiplied by k. Why is it k? E sub r and E sub theta are orthogonal to each other. They're unit vectors. So the cross product of the two of them is 1 times the sine of the angle between it, which is 1, pointed in the direction you get by the right-hand rule. E sub r cross E sub theta points in the k direction. Where would you see it best? is over here. E sub r, E sub theta points in the k direction. On the left-hand side, we have an E sub r crossed with I. E sub r is in this direction. I is in that direction. The angle between them is theta. Right-hand rule points into the board. So E sub r crossed with I is a minus sine theta k. So we get L mg minus sine theta k. Then we take this expression here. We take the dot product of both sides with k. And it tells us that, let's see, the k drops out, the m drops out, and we have theta double dot is equal to minus g over L sine theta. And I believe this is about the quickest derivation of the pendulum equation. So we have a minute for you to ask questions about this. So please look at the algebra and ask questions. Or James, as an expert in the topic, is there something that you think I should have emphasized that I did not? So it's a lot to swallow. I would say if you're paying very crisp, sharp attention, you could follow it. But why don't you just try to ask a question? Which step was unclear to you in what I did? Yes?
Where did you get the sine theta from?
Where did I get the sine theta from? Is I had to deal with an E sub r crossed with an I. And that's what I claimed was equal to minus sine theta k. And how did I get that? Is I used the right-hand rule in this picture, right over here in this picture. Does that answer your question? Any other questions? Yes?
Theta prime is equal to negative theta prime. Are that line over there? Where does the negative sign come in?
Where it comes in, where I said E sub theta dot is equal to minus theta dot E sub r. Okay, there's one key equation, one of these equations that you're just going to know. So let's look at this vector E sub theta here. I'm just doing this kind of intuitively here now, because that's the way you will best remember it. You can go through it more slowly. Here's E sub theta. It's a vector which is spinning around as this thing goes around. If you just look at the vector by itself, when theta increases, E sub theta goes from this to this. So the change of E sub theta is in that direction as theta increases, which is the minus E sub r direction. Just like the change in E sub r was in the E theta direction, the change in E sub theta is in the minus E sub r direction. How big is it? It's proportional to theta dot. So something whose size is proportional to theta dot in the minus E sub r direction, and that's where that equation comes from. Does that address your question? Okay, you have a special guest lecture on Thursday. Good luck to you. See you next Tuesday. My office hours today are going to be done by Pranav. I'm not doing them.